Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, our next talk is Yudong Liu talking about joint work with other colleagues.
Yeah. Okay, thanks everybody. My name is Yudong Liu. Today I'm going to present you my work of using latent support vector machines for semantic row labeling with lexicalized tree adjoining grammar derivation trees. So this work has been accepted by NACO 2010 as a full paper. And this is a joint work with one of my colleagues, Gholamreza Haffar and Professor Anoop Sarkar. So roadmap of the talk. First, I'll introduce you some background knowledge of the work and the motivations. And then I'll introduce you how we generate the LTAG derivation trees. And then I'll present, I'll introduce what is the latent support vector machines. And then I'll present you experimental results and analysis. Then I'll conclude the work and introduce some of my future work. So first, background and then motivation. What is semantic row labeling? So for a given verb, or we call it predicate, so a semantic row labeler aims to identify and label all his arguments with semantic rows, such as agent, patient, and theme. Here is an example from Wall Street Journal where cell is the predicate. So a semantic row labeler basically tries to find all the participants of this action, such as seller, goods, and buyer. So the numbered arguments here actually follow the annotation from PropBank, which is a widely used annotated corpus for semantic row labeling task. So in the supervised learning context, a high accuracy of semantic row labeling system is achieved by first proposing new types of features from different syntactic views, such as chunks, parses, CCG derivations, or dependency trees. Secondly, modeling the predicate frame set between arguments. So in this setting, some illegal predict sequence will be eliminated from the prediction. So third one is to deal with incorrect parser output by using more than one parse. So our work actually falls into the first category, which is propose new types of features from different syntactic views. So basically, we use lexicalized tree adjoining grammar derivations as a novel source of features for the semantic row labeling task. So I assume most of the audience has some familiarity with this formalism. I'll just go through it quickly. So lexicalized tree adjoining grammar consists of a set of elementary trees. And all these elementary trees can be composed together through two operations, substitutions and adjunction operation. And LTAG derivation tree actually used to denote the history of how these elementary trees are composed together. So we are more interested in the LTAG derivation trees where all the elementary trees are included and all their dependency relations are also included in the derivation tree. So our previous work of using LTAG derivation trees for semantic row labeling has been published in EMNLP 2007, where we obtained these LTAG derivations by converting the phrase structure parses. And we propose a novel set of LTAG features and combine them together with the standard feature set, which are extracted from the phrase structure parses. And we feed them into the SR system, and then we get improved performance. So the work I'm going to present today is actually an extension and generalization of this piece of work. So still our previous work. So in our previous work, we use Magman-Collins head percolation rules to get the LTAG elementary trees. All the elementary trees are in spinal form, and we use sister adjunction operations to combine all these elementary trees together. We got the LTAG derivation tree. In the LTAG derivation trees we got, it seems the path feature are less sparse than the path feature in the original path tree. So here, still that example. So in the original path tree, we have the cell as the predicate, and all the red squared nodes are actually the target constituent for the semantic row labeling task. So first, we use the Magman-Collins head percolation rule to get all these elementary trees, and we can see that all the target constituents are actually preserved in the elementary trees. And then we use sister adjunction operation to compose all these elementary trees together into LTAG derivation tree. And then we do the feature extraction as we shown before for the semantic row labeling task. So, okay, here we got some observation. Now we know LTAG features can help to improve SRO performance. And we also found that for a single derived tree, there are multiple LTAG derivations actually available and can be treated as latent structures. So the top LTAG derivation tree actually is used for in our previous work. And here shows one of another possible LTAG derivation trees. So a natural question to ask is that tree definitely better than this one? So this actually motivates us to look at a wider range of LTAG derivation trees and to see which one works best for this task. So our hypothesis is that for different SR instances, possibly different latent LTAG derivations can provide the discriminative features. An LTAG derivation is good if it can provide the LTAG features for a more accurate SR classifier. So okay, that's basically the motivation. So how we generated this LTAG derivation trees? So instead of using a fixed specified set of heuristic rules, such as Magman-Collins head percolation rules, we extended head rule heuristics to generate multiple predicate E-trees and argument E-trees. So basically here, T is the path tree, and X is the predicate, and NP is the target constituent. So we use three fixed heuristic rules to generate the predicate E-trees first. Then that's how we get the P1 and the P2. And we enumerate all possible lexical heads for the argument constituent. And we also list all possible roots. That's how we get the A1 to A6 as argument E-trees. And we also consider up to 3 intermediate E-trees, which locate between predicate E-tree and argument E-tree, as shown as I1 and I2. So, okay, now we got all these elementary trees. We compose them together using a sister adjunction operation into LTAG derivation trees, as shown as like from D1 to D10. And then we do the feature extractions as we did before, and we fit it into SRO learning process. So this is how we generate the LTAG derivations. So in this way, the average number of LTAG derivations per SR instance is around 130. So here, the challenges we face include that we have to face a huge pool of LTAG features. And we need to focus on those discriminative features for each SR instance, how to get all these discriminative features. So our solution is that we use latent support vector machines to do this kind of selection. And we train several binary classifiers using LSVM and combine them using one versus all for the full SR task. So, okay, latent support vector machines. So in our setting, an SRL instance actually is a predicate argument candidate pair. So So the argument candidate actually are all depth 1 node, are all depth 1 nodes taken from the original derived tree. So the point here is that all the candidates are actually collected from the original path tree instead of, they are actually independent of the selected LTAG derivation tree. So latent SVM training is a 2-step optimization algorithm. So first, initialize weight vector W and iterate these 2 steps. First, pick the best hidden structure for each example, and then for each instance, we have the fixed hidden structure, and then we try to learn W for the objective function using some learning method. So in our implementation, H actually is the best latent LTAG derivation tree, and we picked it for each positive and negative as our instance. And we use SVM SGD, which is an implementation of a stochastic gradient descent algorithm. So, okay, experimental results and analysis. So, we evaluated our system on CONLL 2005 shared task release data. And the standard setting is prop bank section 2 to 21 for training, 23 for testing, and 24 for development. And we tested on the full argument set in the shared task. And we use versus all binary classifier. And we use precision recall F-score as the evaluation matrix. And we have a baseline system, which is actually our previous work. And the initial weights for our SVM training are actually from this baseline. So this is the result we evaluate on the CONLL 2005 shared task. So we compare our system with the state-of-art SRL system, which is from Totonova et al. 2008. So as you can, I didn't list it because of the space limitation. I didn't list the full table. You can find that in the paper. So as you can see that the first row is overall score comparison. So our system actually is better than theirs by over 9% on the F-score. So if you look at each individual one, well, this is not the full one. I think except for A5, there are only 4 instances actually in the test data for that A5. So most cases, actually our system performs much better than theirs, and especially for the precision. Sometimes it can reach near perfect, right? So we also done some bit of analysis. So this one shows the learning curve of this model evaluated on the test data across SVM iterations. As you can see that in the first iteration, the performance actually increased dramatically, and then with iterations, the performance actually levels off. And this figure actually shows the change of the unseen derivation trees across SVM iterations. There are 2 things. First, you can see that after the first few iterations, the unseen derivation trees actually drops quite a bit. But the tendency of for the model picking up the unseen derivation trees exists across the whole iterations. So even though it drops quite a bit in the beginning. So this figure shows the number of the distribution of active features over LSVM iterations. As you can see that with iterations, the number of the active features gets smaller and smaller and goes stable. So actually, eventually, we only got after training, after actually I think 39 iterations, only 8K features are selected out of this over 1 million features. So okay, conclusions. Latent LTAG derivations and LSVM provide predictive features and very high precision for the SRI task. So LSVM is able to find features for efficient discriminative learning from latent LTAG derivations. Here we also actually done another analysis for the effect of initial weights. It turns out the initial values of the weights, the feature weights, matter a lot to this method. So current work. So currently, we are working on a log linear model which sums over all latent LTAG derivations per SRO decision. And we are going to release the code and the output of our system on CONLL dev and test data. And we are going to collect linguistic interesting knowledge from the derivations selected by SVM. And also, LSVM, it turns out it's a general learning framework that should be able to potentially apply to many other NLP tasks. Thank you.
Okay, we have time for questions. Questions? You do have to wait.
Thanks. This is really fascinating, and the results you're getting are quite stunning. Just to be clear, the latent SVM, the latent structure that you're searching over, are the different LTAG derivations licensed by the Penn tree bank parse, by the constituency parse. Is that correct?
Well, we obtain all these LTAG derivations by converting the Penn tree bank constituent-based
Right,
parses.
but there are different possible head-finding rules that could lead to different potential LTAG derivations, and you're trying to, like the latent SVM is trying to find the hidden structure that maximizes your binary classification decision, right?
Right.
And so the hidden structure that you're varying here is the LTAG derivation that can be extracted from one Penn tree bank parse or multiple Penn tree bank parses, or?
Well, what we did is only extracted from one Penn tree parse. But I think, yeah, it definitely can be extended to multiple Penn tree bank parses.
Sure.
Yeah.
And there's just a large number of LTAG derivations
Yes,
that are
yes,
licensed by any
exactly.
single Penn tree bank
Yes.
parse. And it's very interesting. Okay.
Yeah, thank you.
Other questions?
So I also was impressed by the results, and I have some questions on the evaluation that you.
Yeah.
So this decision of using the portions of the prop bank from 2 to 20 to 21 for training and then 23 for testing is something that is standard?
Yeah,
or?
it is standard. That yeah, that's the standard benchmark data.
Oh, okay.
Yeah.
So you don't do kind of a cross validation on all the portions by
No,
training?
I didn't do
Do you know why? You do?
that.
Why people
well,
don't use this particular one for testing?
Well, we because for the comparison purpose, we just follow we didn't use other procedure. We just follow the standard procedure to get the result, and we use section 24 as a standard way to do the development instead of do other cross validation.
So Tutanova did the same?
Yes.
Like this. Okay. All right.
Yeah.
I have a question. Like, why is VM not logistic regression?
What is that?
Why SVM and not logistic regression?
SVM is not.
No. Why you are applying SVM?
Oh, why?
Yeah.
Actually, this work also enlightened by Colin Cherry's work, and
Yeah.
I think also Chris' work. They use some latent structures, use latent SVM, apply it on the NLP task, I think language learning task, with latent by treating parse trees as the latent structures.
Yeah.
I think that scenario actually is quite fit with our scenario.
Oh, okay.
So actually, this idea actually is enlightened by their work.
So you cannot apply logistic regression on this?
Well, yeah, we are
latent
working
structure?
on that.
Yeah, and like so far I know that in SVM, it does not have this sound probabilistic interpretation. And also, like when you do like on versus wall, you have one area that is undecided.
Mm-hmm.
So still, it has some problem. So
Well, we see this LSVM, but actually we choose this so the learning framework, as I showed you before, is you can feel free to choose other learning method.
Yeah.
So the framework is actually the same, but the learning method you can feel free to choose. Yeah.
Okay.
Questions? So I have a question. Oh.
Just a brief one, if nobody. Just in terms of the data, you're commenting how little data there was relating to A5. You know, for when you're taking a look for the different arguments and that. Just if you want to pull up that slide, if you just want to say relative proportion, like when you're going A0 through A5, just to give everybody a sense of the problem, like how large of sets you were dealing with there relatively. Can you just briefly say that?
Yeah, actually, in my paper, it shows the like what's the number for each argument. So you can definitely look get the idea from there. So for A5, yeah, the number is pretty small in the test data. It's only for 5, I think. But yeah, the whole result, including all those numbers, actually can be found in the paper. So I won't list them here. Yeah.
Questions? I have a question. So can you talk a little bit about the precision recall imbalance in your system? And is there any way in which you could try to find another operating point where you might balance those a bit? It would strike me that if you could just get your system to predict a little bit more, you might, it's doing a pretty good job up to that point, you might reach an overall better F measure spot. And if you can't straightforwardly, then this may be a limitation. And otherwise, also, could you comment on why is the precision high relative to recall in your system in particular?
I think the recall upper bound actually is decided by the way we select the candidates, right? So as shown you before, I think it's here. So the way we choose the SR instances basically based on, I think, the explanation there. So all the depth 1 node taken from the original derived tree. So actually we use some heuristics to collect the candidate nodes first. Basically this way, I think set upper bound of the recall. So if we don't change this, so it's hard to reach a higher recall.
I see. So this is related to Chris's point earlier that you could, in principle, generate k-best output from, say, the
Yes.
tree bank parser, generate more candidate
Yes.
arguments, and thus have more flexibility in tuning
Yeah,
your...
that's definitely one of
Okay.
the ways to improve
Fair
the
enough.
recall.
Okay.
Yeah, and also for the question of why this method works so well. So I think this is the things we've been keep seeking the answer for. So I think first this is a typical thing that everything works together pretty good. So there are several things, as I said. It seems like all these LTAG derivation trees do contain all the discriminative features. So, and if we expand the size of the the derivation trees, it may bring in more good features, which can improve the performance. So this is one thing we definitely can say. And the other thing is it seems like LSVM, this learning method, we didn't actually put a lot of efforts to tune the parameters. But it seems like, yeah, it works pretty well with this kind of setting. And we also actually, in the paper, we also collect a lot of statistics to see why, like what kind of LTAG derivation trees that the model actually picked up. So we see that in some cases, well, for example, for identification, in a lot of cases, the model actually try to localize the predicate and the argument more closer. So like in the trees, the model picks, it seems like these two things are closer to each other. So they have shorter paths, between them. So yeah.
Other questions?
We also give some example in the papers, actually. You can get more information from there.
Other questions?
Can you go back to the slide showing performance as a function of iteration count?
Okay.
Because you get this huge jump from iteration 0 to 1, right? And I mean, this is what Colin and I saw as well, I think.
So the analysis part, right?
Sure. That's our guy, yeah.
This one?
Yeah, exactly.
Okay, yeah.
So now, and an iteration for you is doing, I mean, you can look at latent SVM as kind of this coordinate ascent where one direction is over my hidden structure and the other is over my weights, right? So an iteration here, the latent structure has actually changed from your initial latent structure, right?
No.
Iteration 0 is using the baseline latent structure, and iteration 1 is using a new latent structure?
That's right.
Yeah.
That's right.
And so most of the bang for your buck is happening on that first round.
Exactly. Yeah, in the first few iterations, actually, then it goes stable.
Yeah.
Yeah. I think also shown here.
Yeah.
So it seems like the trees actually keep unchanged.
Yeah. Well, they change for much longer than the performance boost happens. You know? It feels like it's twiddling fine parameters at that point. But yeah, that's interesting. And do you think? Do you have any idea about how important your starting point is? Because that's something that.
Yes, actually, I should have shown that slide. I think I have it some. Oh, sorry.
I mean, the theory behind latent SVMs is that you get nice convergence properties.
Yeah, we did some analysis on the effect of the initial weights for this. I think I have it somewhere.
In the long form.
Please. Yeah, I think probably it's here. Let me see. The initialization, right? So you're talking about the initialization. Yes, we did some initialization analysis. We randomly for each SRL instance, we randomly pick a derivation tree from the pool, from his derivation pool, and we get some initial weights, and then based on that weights, at the initial point, we do the SVM iteration. It seemed like the performance actually not as good as the baseline. The baseline basically is we purely use Magman-Collins head percolation rules to do the SVM training. So,
believe it or not, we still have time for questions if there are short.
Now I cannot remember if you already said that in your future work, but I was wondering if you had to apply this approach to another NLP task. What would be the next that you think would benefit from that?
Well, actually, for now, we are focusing on the on still the same setting, but using the log linear model. But another one, probably, we're thinking use it for parsing, for LTAG parsing. Yeah.
And I'm going to sneak a quick one in. Maybe, Nate, you can go to set up so we transition. But the last question I had is, I don't quite understand. So is it that you derive the dependencies, the elementary trees from the tree bank parses, and then you reassemble them?
Yeah.
Or are you, so one way in which you could use head percolation is you take a parse and it corresponds to a dependency graph. And then you're stuck with that dependency graph. You're instead breaking it apart and reassembling it.
Yeah.
Is that a costly process? Can you talk about how expensive it is? Is that a bottleneck in time? To actually, so you are doing an LTAG parse.
Well, actually, we are more interested in each elementary trees and their dependency relations. That's all.
Correct, but you still have to. Okay, but I see. So you're deriving those, and then that's it. You're not reassembling them.
No, that part is not actually quite useful for us.
Okay.
Yeah, thank you.
Okay, let's thank the speaker.
Thank you.
And the last talk of the day is Nate Bodenstab talking about joint work with me and Keith Hall from Google on some fast heuristic parsing techniques.
Hi, my name's Nate. I'm going to be talking about a method called exponential decay pruning, and the goal is to do syntactic parsing very quickly and still retain your accuracy. So the outline of the talk today, I'm going to give a brief intro to syntactic parsing just to catch everyone up. Maybe it's been a while since you programmed your CYK algorithm. Then we're going to talk about a couple of these. We end up using a beam search in the end, which CYK and best first kind of naturally lead into a discussion of the beam search for parsing. And then I'll explain our exponential decay pruning. So this is a parse tree. This is what we're trying to derive using parsing algorithms. I mean, it's a hierarchical clustering and labeling of these syntactic constituents here. Hopefully we're all somewhat familiar with this. Why parse? Pick your favorite NLP application and somebody's tried to apply parsing to it. Machine translation, language understanding, language modeling, and as Brian keeps trying to remind me, it's fun. So what do you need to parse a sentence? Typically, supervised data, a tree bank, which is a collection of sentences with manually annotated parse trees. Of course, people do unsupervised parsing, but that's much more difficult. From this data, you can induce a binarized probabilistic context-free grammar. And once you have that, you can plug it right into your parsing algorithm and go to town. So an example of some of these grammar rules, for instance, might be this S goes to NP-VP. That's a sentence. Non-terminal goes to a noun phrase and a verb phrase with some probability. We also want to make sure the grammar is binarized, which means if you have more than two non-terminals on the right-hand side here, you can decompose it into a few more rules such that all of the rules you have are binary. So in the past 10 years or so, there's been some significant accuracy improvements in parsing, and a lot of that comes from grammar refinement. And the motivation behind that is if you take a straight Wall Street Journal tree bank and you induce a grammar from it, they're going to have simple categories. For instance, there's going to be one noun phrase category. But as we know, noun phrases act differently in different contexts. For instance, the subject NP versus an object NP. And we want to be able to model those distributions separately. So what people do is they split these categories into into more categories, and we can estimate the probabilities more accurately. So if you have your basic grammar induction from the tree bank, you're going to have something like 64,000 grammar rules. You're going to be able to parse pretty fast, maybe like 10 sentences per second, 0.1 second. But you're going to be in the mid-low 70s as far as accuracy goes. Johnson proposed this method called parent annotation. And I'm not going to go into the details of these, but the trend here is that we're going to increase the grammar size overall, which is going to make our accuracy better, but it's going to take much longer to parse. The grammar we're going to focus on here is this latent variable grammar from Petrov when he was at Berkeley. And this is automatic splitting of these categories. And in the end, you have a very large grammar, 4 million rules, but it's an explicit grammar, which is nice to work with. And you're high accuracy. You're about to 90%. The bad part is if you use your generic CYK algorithm to exhaustively parse with this grammar, you're going to be waiting around a long time. One sentence is going to take you over a minute to parse. So a little more details about this, about the latent variable grammar from Petrov. Like I said, it's automatically, these non-terminals are automatically split into subcategories, and these subcategories are just explicitly annotated onto the non-terminals of the grammar. So you have a sentence in category number 3 out of, say, 12. And the Berkeley also has a parser that uses this grammar, and it's a course-defined parser. And how it works is they have 6 levels of grammars, from a small grammar to a very large grammar. One is less accurate all the way to more accurate, and they parse the input sentence completely. Well, they parse the input sentence once with each of these grammars. And as you get more and more accurate, they use the posterior probabilities from the previous parse to prune the parse space in the subsequent parse. And they actually get some really good results. So the course-defined algorithm's a nice thing. One downfall of this approach is that when you're transitioning from grammar n to grammar n+1, you have to have some correspondence between the non-terminals in these grammars to know that if I have a noun phrase 1 from my second grammar, that's going to prune noun phrase 2 and 9 in the subsequent grammar. So the goals of our research is to find good solutions very quickly in this large grammar space. And it's very large if we use one of these large grammars. It's not necessarily finding the maximum likelihood solution, but just something good. We also want to come up with algorithms that are grammar agnostic. So we can switch out any grammar we want. We can do different grammar transformations and still run in with the same algorithm. We also want to consider practical implications like speed and memory, which sometimes we tend to ignore. And in this talk, it's about exponential decay pruning, which I said uses a beam search parsing, which I'm going to talk about. It does search the final grammar space directly, so it doesn't need to know anything about the grammar. And it ends up balancing the overhead of this targeted exploration from like a best first search, which I'm going to talk about, versus the memory and cache benefits of a local exploration. And when I say cache, I don't mean like memory cache necessarily, although that helps, but different features that you're computing for a localized area in the chart. So now I'm going to step through a couple of these algorithms real fast. The CYK algorithm, you have your parsing chart here, and what it does is it exhaustively populates all parse trees using a dynamic programming algorithm. And in the end, you get the maximum likelihood solution. So we start at the bottom. We seed it with all the part of speech tags for each of these words. And then we take all rules in our grammar and we apply it to the, well, we stick in these grammar rules where it's appropriate within the chart. And we work our way up the chart going from spans meaning it covers that many words. So a span of 3 would cover 3 words. And we build all the way up to the top. Also note that when we're filling entries into a cell with a binary rule, we have to consider which span the left non-terminal covers and which span the right non-terminal covers. So effectively, we have to check every single one of these midpoints, which is another n iterations, which makes CYK algorithm kind of slow. On the opposite end of the spectrum, we have a best first search. And what this does is it's a more directed search in the space. We maintain a priority queue, which is the frontier, the kind of the exploration frontier of chart entries. So how this works is the frontier contains all possible all possible entries we can traverse to in the next step. The frontier is ranked by an objective measure that ranks cells on how likely they will participate in the final parse. And we simply pop the best edge off the frontier at one step. We place it into the chart, and then we add all possible future edges back onto the frontier. And as you can see, you come out with a chart that's obviously not exhaustive. It's a much better traversal through this space. But the downfall is that you have to maintain this very large priority queue. So you can have millions of edges in this that you're constantly keeping sorted. So I mentioned this frontier ranking function. People call that the figure of merit. What you're doing here is for an entry in your chart, you have a measure of the merit from the inside probability here. That's how well this constituent covers this span. And then you also have a heuristic estimate of how well this non-terminal is going to participate in a final full parse. So we call this the inside probability, and then this the outside probability. The inside we get from our grammar rules. The outside, there's various heuristics to estimate that. In our setup, we use Carabello and Charniak's method for estimating the figure of merit, which works pretty well. One problem is that within this global frontier priority queue, we're comparing constituents from all over the chart. So if you have a good constituent here that covers a span of 2, and you have a good constituent here that covers a span of 4 or 5, I mean, how are those really comparable? But we're forced to compare them within this global priority queue. So that leads into beam search next. And beam search for parsing, I think, is kind of the best of both worlds. How it works is we do an exhaustive cell traversal in the chart. So we're going to enumerate all of these cells as the CYK algorithm does. But in each cell, we compute the figure of merit for all possible cell entries. Then we stick those into a local agenda or local priority queue. And then we only pop off the top n to populate the chart cell. And this is called the beam width in beam search speak. So what's nice about that is we can then throw away all the rest of the entries and move on to the next cell. The benefits here are that it's less memory. You're not storing the exhaustive cell entries like CYK does. Plus, you don't have to store this large global priority queue like best first does. It runs faster because you're pruning the search space, unlike CYK, and you don't have to maintain this sorted priority queue during your parse. Plus, it's eliminating the problem of the global cell entry comparison because you're only comparing constituents within the same cell, meaning within the same span. So that leads into exponential decay pruning. When you're doing a beam search, kind of the natural question to ask is, what is the optimal beam width? So when you're in a cell and you have a ranked list of entries, how many of those entries should we actually put into the chart? Common solutions are a relative score from the highest ranking entry. So if you have maybe 2 really good entries and the rest are really bad, you'll only retain the top 2 because there's such a probability difference there. Also, there's a global maximum. So somebody will just say, our beam width is 10, and in every cell, we're just going to put the top 10 into the chart. What exponential decay pruning does is it creates an adaptive beam width, and it's conditioned on information about the chart cell. Another way to think about this is how reliable or how much do we trust our figure of merit, depending on where we are in the chart. So what I did was I plotted the rank within these local priority queues within the frontiers of the gold entry, which we know from the supervised data, against the span and the sentence size. And what I found out was that our figure of merit is more reliable for larger spans, meaning the gold entries are ranked towards the top when the span gets very big. And this is probably because it's less dependent on that outside heuristic that we have to estimate. I also found out that the figure of merit is less reliable for shorter sentences, meaning that the gold entry was kind of farther down in the list. And I'm guessing this is because of the kind of atypical grammar structure for these short sentences, especially in the Wall Street Journal tree bank, which you run into like list items and stuff like that. So this confidence in our figure of merit can be modeled with the exponential decay function. And what that, how you compute this value, you need the initial beam width. Like I said, this is the global beam width somebody might set, say 10 edges. And then that number of edges decays depending on your sentence length, on your span length, and then on a tuning parameter lambda. But instead of trying to visualize this equation, here's an example. So the baseline, the constant beam width, with this green line across the top. And this is a percentage of that constant number. So this is the new beam width, or at least a percentage of the new beam width. And the x-axis here you can think of as a ratio of the span length to the sentence length, so relatively how high you are in the chart. So for the shorter sentence, this is a sentence of length 5. We see that we start there and slowly taper off. So by the time we're at the top of the chart, we're still adding half of the global number. But in these very large sentences, like a 40-length sentence, we actually cut the beam width down very rapidly. And we can get really big savings from this and still find really good parses. So results. As in the last talk, we train on the standard sections, 2 through 21. And then there's the dev set and the test set. In our experiments, we also use this Berkeley latent variable grammar that I talked about. We use the Carbell and Charniak figure of merit, which I haven't given any details about this. I have a couple slides at the end of the talk if people are interested. And then we also apply this technique called cell closing constraints from Brian and Christy Hollingshed a couple years ago. And what this technique does is it actually ends up being complementary to ours. It takes features of the sentence and completely blocks off certain cells in the chart. And I'll show results with this as well. And then in the end, we do an external comparison with the Berkeley course-defined grammar. They use the exact same grammar that we do, so I find this as a nice comparison point. So there's the algorithm over here. This is the baseline CYK algorithm. It takes about 94 seconds per sentence with this grammar, and we're in the high 80s as far as F-score goes. If we use the best first search with this global agenda, it's actually quite a bit slower than the exhaustive search, even though we're pruning some of the space. But we do find the same solution in the end. Using this figure of merit, the CNC figure of merit, we get a huge savings in speed, couple orders of magnitude, but we also hurt accuracy a little bit. We're getting to a solution really fast, but it's not the best solution. So applying a beam search, first experiments we did was with just the simple inside probability, meaning that our figure of merit is just the grammar score, and there's basically zero probability for estimating to the end. We see that with the inside score, we're at 5 seconds per sentence, which is way, way faster than the best first score. Plus, we're still retaining the accuracy here. So beam search is a huge savings over best first. Plus, if we use the exponential decay pruning instead of this constant value across the board, we see an additional almost 50% reduction in the speed. Then we apply the CNC figure of merit, and we see similar results, but much faster again. We're still in this high accuracy ballpark, but we're way faster than beam search. We're way faster than best first search, and the exponential decay adds another 40% speed up here. And then, like I talked about, there's this cell closing, which will block off individual cells in the chart that we just skip entirely. And this is quite complementary. We see quite a bit of additional savings, even when we use the exponential decay. So taking the best setup and applying it to the test set. By the way, these results were from the dev set. For the test set, we see that our baseline CYK algorithm is very, very slow. Using the beam search, we still are seeing around a 40% improvement between the constant beam width versus the exponential decay beam width. And then again, when we apply these cell closing constraints, we get additional savings, and we actually get a little bit of an accuracy boost too here. And then comparing it to this external Berkeley course-defined parser, we get the same accuracy, and we're just a tiny bit faster, but I'm going to call it about even. The big benefit here is that doing this exponential decay with the beam search is a very, very simple algorithm to implement. And plus, it requires no knowledge of the underlying grammar, which I find is two big pluses. So this is kind of a first step in the direction of our overall goal of parsing very, very quickly. And I feel that these results are promising, which is always nice to work on a project that feels promising. So we think we can speed this up quite a bit faster. And once you're parsing at 50 sentences a second, that makes parsing very practical to a lot of applications. So that's it. Thanks.
Okay, we have time for questions.
Have you thought about combining your parsing method with course-defined parsing and might get even faster?
Yeah, that's not a bad idea. I haven't really thought about that too much. Just trying to think how that would even work. So how course-defined works is you parse with a very simple grammar, and then you do the inside and outside probability estimation. And then when you do your next grammar, you prune not only cells, but also chart entries within those cells. So you're saying of the remaining cells, maybe you could, or of the remaining entries in that, maybe you could prune that even farther. Yeah, that's an interesting idea.
I mean, you really are doing course-defined parsing.
Yeah,
without admitting it, because the cell closing pass is just the coarsest possible pass.
Yeah.
How is it that cell closing gets you an accuracy increase? Do you expend the resources that you saved looking more deeply at the other cells?
Yeah, so it's not just the cell closing. We also find a small increase with the exponential decay as well. And why we think that is because you're getting the cell closing takes some more contextual information that's richer than perhaps the grammar provides, and it's pruning these bad options early on. And so you're left with more feasible options in your beam width for later parses.
So
Yeah.
I had basically the same question. If I understand this right, that accuracy increase means that those are cases where the most probable parse is actually the wrong one, and you're not finding the most probable parse because you've pruned it. So
Right.
have you looked at those examples to see if there's something in particular going on in linguistics? I'd just be really curious on the error analysis there.
Yeah, that means the maximum likelihood parse tree isn't the best parse tree. So there's probably some deficiencies in the grammar there, and fixing that's a great idea. But I haven't looked at those examples specifically.
I'm resolved not to jump in on such discussions. However, this is related to the other papers that Christy and I had, and we observed this also when we applied it to the Charniak parser. In that case, we did analyze. It is a mixture of model errors and search errors. We're sort of fixing a little bit of both. In this case, I suspect it has to do with fixing model errors, just because the search errors are localized is different than the Charniak parser. But if you think about it, you're using it. I'm sorry, I'm using your time, but as I usually do. You're using a lexicalized tagger, and so you're using sort of sequential information, which tends to sometimes be lost in the grammar in the way the dependencies are used in the grammar. So it's complementary. That's pretty much why. Other questions? All right, let's thank the speaker.